In this lesson, you're going to learn about chords and arcs of a circle. The objective is to use congruent chords, arcs, and central angles and perpendicular bisectors to chords. So let's look at some definitions here. The first one is the definition of a chord. A chord, C-H-O-R-D, is a segment whose endpoints are on a circle. So let's draw a little example in the margin here. I could have a chord that, as long as the endpoints are on the circle, is a segment whose endpoints are on the circle. That's a chord. Now, if the chord happens to go through the center of the circle, so if I have another chord here that goes through the center of the circle, then that chord is also a diameter of the circle. So let's look at, there's several theorems and converses to several of these theorems. Each one of these we need to be sure and draw a diagram for each theorem to illustrate it, to make, so you can understand it, make it more clear. So the first theorem says within a circle or in congruent circles, congruent central angles have congruent arcs. And the converse of this says that within a circle or in congruent circles, congruent arcs have congruent central angles. So let's look at a diagram of this. You have a circle and you have two central angles. A central angle is an angle whose vertex is the center of the circle. So here, let's say we have central angle AB, and then we have another one that is CD. So here we have two central angles that are congruent. So we have angle AB is congruent to angle CD, which means that arc AB is also congruent to arc CD. Let me put the arc in a different color so you can see arc AB is on the circle and has the endpoints of those two radii, and they're A and B, points A and B, and then C and D are the endpoints of the other arc. So we'll call this circle O. So let's go to the next theorem. In the next theorem, it says within a circle or in congruent circles, congruent central angles have congruent chords. The converse of that is also true. Within a circle in congruent circles, congruent chords have congruent central angles. So let's draw the diagram in the margin again. Got a circle. Call it circle O again. We have our central angles AB and central angle CD. Those two central angles are congruent. So that means that the chords that connect A and B, there's a segment connecting A and B, that's the chord, and then there's a segment that's connecting C and D, and that's chord CD. So the congruent central angles have congruent chords. So here central angle AB is congruent to angle CD, and chord AB, which is a segment, is congruent to chord CD. In the next theorem, it says within a circle or in congruent circles, congruent chords have congruent arcs. Converse of that's also true. Congruent arcs have congruent chords. Look at the same type diagram here. We have circle O again. Only this time we have congruent chords. So if I have chord AB and I have chord CD, and those chords are congruent, that also means that the arc AB has to be congruent to arc CD. So we'll write that below here. If we have chord AB, which is the segment, it's congruent to chord CD, then that means that arc AB is congruent to arc CD. And the converse of that is also true. The next theorem says that within a circle or in congruent circles, chords that are equidistant from the center or centers are congruent. They're congruent chords. The converse of that is also true. Within a circle or congruent circles, congruent chords are equidistant from the center or centers, if you're talking about congruent circles instead of just one circle. So in this diagram, got a circle, got our circle O again, and if we have chords that are equidistant, so if they're equidistant, how do we draw that? If we have a chord, equidistant means that the perpendicular distance from the center, so that perpendicular distance, we'll draw another chord on the other side, and we'll draw another chord perpendicular distance. If those two distances from the center are congruent, they're equidistant from the center, then that means that those chords have to be congruent. Next theorem, in a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Look at a diagram of this one. We have our circle O again. So if a diameter is perpendicular to a chord, so we have a diameter, which is a chord that goes through the center of the circle. If diameter is perpendicular to another chord, so we'll draw this other chord and it's perpendicular. The diameter is perpendicular to that chord. Then that means that it bisects that chord, so I'm going to put congruence markings on the chord, and it bisects the arc, so I'm going to put congruence markings on the arc as well. It bisects the chord and it bisects the arc. In the next theorem, it says in a circle, if a diameter bisects a chord that's not a diameter, then it is perpendicular. To the chord. Same diagram, circle O. So if you have a diameter and you know that it bisects that chord, then that means that it has to be perpendicular to that chord. The diameter has to be perpendicular to the chord. And where this will come into play in some problems is that that gives you right triangles that you can do calculations with, knowing that that's perpendicular and you have a right angle there. The last theorem says that in a circle, the perpendicular bisector of a chord contains the center of the circle. So here if we have circle O, and we know we have a chord and we have a perpendicular bisector, it bisects the chord and you know it's perpendicular to it, then you know that that segment, this segment here, has to contain the center of the circle. It has to be a diameter. So we'll use that in some problems. So let's go look at the right side of the page and work some examples. In problem 1, we're using congruent chords. In the diagram, it indicates that segment VT is congruent to segment RP. So put some congruence marking there. And what can you conclude from that? Those are chords of the circle, and they're congruent chords. So what can you conclude from that? You can conclude that if the chords are congruent, then the associated arcs are also going to be congruent. Arc VT is congruent to arc RP, and those central angles are also going to be congruent. Angle VDT is going to be congruent to angle RDP. In problem 2, you're supposed to find the value of A in the circle. So if you look at this diagram and find which theorem relates to it, you know that this segment here is, since it goes through the center of the circle, it's a piece of the diameter, and the length of it is 7. And you also have another one that's the length of, it's another piece, a segment of another diameter that's a length of 7. So you know that those two are equidistant. So these chords, these two chords are equidistant from the center. And it also has perpendicular markings there. So that indicates that this diameter is perpendicular to that chord. And if it's perpendicular to the chord, the theorem over on the left side of the page says if a diameter is perpendicular to a chord, then it bisects the chord. So that means that if this side of the chord is 6, then A has to be 6 as well because of that theorem. In the next question, finding the center of a circle, it says, given an arc like the one below, how can you find the center of the circle that contains the arc? So how can you find it is the question. And all that you have is an arc, which is a piece of the circumference of a circle. So what you would have to do is, based on the theorems that we have, the last theorem on the page says that in a circle, the perpendicular bisector of a chord contains the center of the circle. So that's how you would have to find the center of that circle. You would have to draw two chords. So that was your first step. We'll look at just a couple of steps. First step would be to draw two chords. in the circle. So I'll just sketch in 2 chords in that circle. And then you would have to construct a perpendicular bisector to each one of those chords in order, and where those 2 perpendicular bisectors intersect is going to be the center of the circle. So let me see if I constructed a perpendicular bisector to one of those arcs, and then constructed a perpendicular bisector to the other of those arcs, the point where they intersect is going to be the center of the circle. So the second step was to construct a perpendicular bisector to each chord. And that's, like I said, using that last theorem, where they intersect is going to be the center. So that answers the question, how can you find the center of a circle that contains that arc? Let's look at the last problem. In the last problem, you're supposed to find the missing links to the nearest tenth. So look at the information they give you in the circle. They give you a segment that goes through the center of the circle, so that segment is a piece of the diameter of the circle, and the diameter is perpendicular to this chord that's length 12. So according to our theorems, that tells us that if a diameter is perpendicular to a chord, then it bisects the chord. So that means that each of these segments, the 12 is bisected into 2 lengths that are 6. So now you have a right triangle that you can calculate the hypotenuse of this right triangle. So use your Pythagorean theorem. C squared is a squared plus b squared. Your hypotenuse is the x. It's opposite the right angle. And then the legs are a and b. So you have 6 squared plus 5 squared. So here you have x squared is 36 plus 25. X squared is 61. Take the square root of both sides to the nearest tenth. X is equal to 7.8. In the problem below, the B part, you have a radius of the circle. You have a piece of a diameter again that you're looking for. This segment is a part of a diameter because it goes through the center of the circle. And you know that it has bisected that chord because the lengths are 5 and 5. That tells you it has to be perpendicular. This one of our theorems over on the left says if a diameter bisects a chord, then it's perpendicular to the chord. So we know that that is a right angle. We know that we have a right triangle. So the question is, how do you calculate x? I know that one leg is x, one leg is 5 of the right triangle. What is the hypotenuse of that right triangle? Well, the hypotenuse of that right triangle is the same as a radius of the circle. And the radius of the circle, if we look at that again, the radius of the circle is 9. So that means that the hypotenuse of that triangle is also 9. So let's use the Pythagorean theorem again. C squared is a squared plus b squared. This time your hypotenuse is the 9. So 9 squared is equal to the legs are the x and the 5. X squared plus 5 squared. So you have 81 is x squared plus 25. Subtract the 25 from both sides. X squared is 56. Take the square root of both sides. To the nearest tenth, x is equal to 7.5.